Everybody, we've got a fun section looking at volumes. Sounds intimidating. There's going to be quite a bit of theory before we get to a bunch of examples. So 6.2 part 1, volumes using disks. Let's check it out. We're going to start with this, kind of reflecting, thinking about finding areas between a function and the x-axis. To find an exact area, think back, like, what is our strategy? We're thinking of adding infinitely many, infinitely narrow areas. And we went about that thinking about rectangles, right? So there were infinitely many rectangles. All of them were infinitely narrow. If that's the way we would find area, then how do we take it to the next dimension to find volume? It's actually a very, very similar approach. To find an exact volume, we add infinitely many, infinitely narrow volumes. So we think of all of these infinitely thin volumes. When we add them all together, they're going to create a three-dimensional shape. And we'll end up finding the volume of that three-dimensional shape, I guess. We're going to use this general way of finding that volume. V equals the integral from a to b, a of x times dx. So right in the original definite integral, we had a function here, which was like the height of our rectangle. We had the height times a width. Now we've got an area, a of x. If we take an area times a width, then that creates a very small little volume. Technically, a of x is a cross-sectional area. So we'll see what that looks like in some drawings here in a second. And the dx, again, is an infinitesimal width, a very, very tiny little infinitely small width on our area to create a tiny little volume. And the integral adds up all of the infinitely many volumes starting at A and ending at B. Okay, let's apply this section. So this formula you see, this is like the general volume integral formula. We're going to see that again in 6.2 part 2. But here in part 1, we look specifically at what we call a solid of revolution. A solid revolution is the solid created when a function is revolved about an axis. It turns out solids of revolution are simpler than doing just volumes in general, which could be anything. So we'll start with the solid of revolution. What does that look like? So think about a function that is being rotated or revolved about an axis. Here's what that would look like. So here, we got just kind of any old function, right? Starting at A, ending at B. We're going to think of that as spinning. And let's, for now, let's just do it around the x-axis. So think about that orange line, just the part between A and B, rotating around the x-axis. How would you draw that? What would that look like? So you could draw what's happening at the endpoints, right? It's spinning around, and then we'll have that middle section spins around as well. And maybe if you try really hard, you can imagine what that 3D shape is. So I kind of think of these left sides as coming out in front of the x-axis. And then as it spins around, this goes back behind the x-axis and comes all the way around, right? So if we were to like rotate it and look at it straight on, those would be circles. Okay, so maybe you can kind of imagine that three-dimensional, it's sort of like a Coke bottle sort of a shape, a little bit. Okay, how are we gonna find the volume of this thing? Well, the key is, right, our formula up above, the key is to find the cross-sectional area for a solid of revolution. So let me draw a cross-section Here somewhere in the middle, again, it's like that. It's coming out in front and then tucking back behind and all the way around. We're just going to do it at some, any old place between A and B. We'll just call it X. Well, the idea is to find the area of that circle. So we can note the radius of the circle. If it's happening at X, we'll call the radius R of X. Notice that the radius will be a function of X because the radius is going to change as we move X values starting at A and ending at B. Those are all going to have a different radius for every point we take. How do we find the cross-sectional area? How do we find the area of that red circle? Well, if you remember, it's the area of a circle, pi r squared. Oh, there it is colored in. Okay, so that's the cross-sectional area we're looking at. Perfect. The cross-sectional area is a circle. So we would say that A of X equals pi r squared. Obviously, we're going to use R of X. So pi r of X squared. R of X will be a function of X. That we'll have to find. It'll be part of the examples that we do. Hey, so this is really great. For a solid revolution, we realize just the nature of it revolving, the cross-sectional area is always a circle. So we can always use pi r of X squared. So we're going to take this, and to get a formula, we're going to take this right there. We're just going to put it in for A of X. So here we go, same image. The integral from A to B, pi r of X squared dx will be our volume. Notice we can write that just a little bit better, that pi is a constant. So let's go ahead and pull the pi out in front and say our volume equals pi times the integral from A to B, r of X squared dx. Just a note, we are going to refer to that formula and the image that we have above. This is the disk method. There is going to be another slightly more advanced method we're about to talk about. We'll think of the disk method as being right because that cross-sectional area kind of looks like a disk, like a frisbee or something. Okay, what's the slightly more advanced version? Imagine two functions, and all we want to do is rotate the area between them around, let's say, the x-axis. So just imagine that area between F and G as we're spinning around. So it's going to leave this hole in the middle all the way through, in this case, all the way through the shape. Let me try to draw that. By the way, when we actually do questions, you won't need to draw these. It's just useful here as we're developing the idea in the cross-sectional area. Okay, so just the area between those functions is revolving. What would that look like? Okay, so we'll need to draw a circle around like where the f of x would be rotating, and then again where the g of x inside of that, right? And if we draw the other pieces, so I tried to create this as symmetrical as possible. It's all right. It's okay. I think we can imagine. Okay, so we can see, there's the full volume, but then there's this space going through the middle. Interesting. Okay. What would a cross section look like? Maybe something like this. Again, there'd be two circles. Okay, with that hole in the middle. Let's do this. We'll fill in that cross-sectional area. But in order to figure out what the area of that blue region would be, let's look at it straight on. So let me create that circle again, that cross-sectional area. But looking at it head on, I think we can get the area a little bit easier if we do it this way. how are we going to get the area of that blue zone, right? We want the area that the solid would take up, but we want to avoid calculating the area of the hole in the middle. Here's what we can do. We can find the area of the entire thing and then subtract the area of the center. And we'll have the area of the outer part. So we draw a radius to the very outside edge and then to the inner edge. We'll give these two different names. We'll call the outer radius capital R of X, and we'll call the inner radius lowercase or little r of X. Okay. So what is that cross-sectional area, that blue area? Well, here A of X, right? We're going to take the area of the entire of the big circle and subtract the area of the little circle. So that would be pi capital R of X squared minus pi little r of X squared. And if we put that into our volume formula, notice that we can factor the pi out completely in front of the integral. So the volume will equal the pi times the integral from A to B, and then capital R of X squared minus little r of X squared times dx. This sort of situation, we're going to give a different name. We're going to call this the washer method. A washer has this sort of a shape like the cross-sectional area. If you have, think of like a screw or a nut, right? A washer, well, has that sort of a shape. If you work with many hand tools. Okay. So notice though, I mean, once you have those functions, right, it looks really complicated, but once you know what these functions are, you plug them in, you just do a little simplifying, and there you are. Okay, hey, we're ready for examples. I think we're going to get to these in the next video, but at least let me just kind of present them here. Find the volume of the solid formed by revolving the region bounded by the curves about the indicated axis. So, when they give us a problem, they're just going to tell us, very much like in the last section, they're just going to tell us a few functions. We'll need to figure out what the region is, and then we'll figure out how to revolve it about an axis. So most of the time, an axis is either going to be the x-axis or the y-axis. Notice here in part E, we're going to revolve about a different line other than the x or y-axis. So we'll see a lot of stuff here. Okay, I'm going to go ahead and stop. We will get to a couple of those examples in the next one.